So at this point, we should have a pretty good idea of what the derivative is and kind of an idea of what it's telling us and how to interpret it. But up to this point, we've really only been able to compute derivatives by using the limit definition of the derivative, which we do need to still make sure we remember how to use that and what it's telling us. But it'd also be nice to have some simple rules to save us a little bit of time when taking derivatives. So that's what we're going to start with this section, is kind of getting some basic function derivatives so that we don't have to use the definition every time. Okay, so we're going to start building a library here of functions whose derivatives we know what they are. So one thing to keep in mind, it is important that you still remember the limit definition and understand what it's telling you. So it's giving you the slope of the tangent line as a limiting value of slopes of secant lines. That's very important to remember. And remember how to actually evaluate that, because not every function will have a shortcut. Sometimes you do have to actually just resort to the definition to calculate a derivative. So let's start with the simplest possible case. So let's let c be a constant, and we're going to evaluate the derivative of f of x is equal to c. So intuitively, we know the derivative is measuring how a function changes, so like the y values of the function as you change x. So if we have a constant, as I change x, the output values don't change because it's a constant. So intuitively, we should expect that the derivative would be 0. So let's go ahead and verify that with the definition. So recall that the derivative at x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. But in this case, no matter what you plug into f, you just get c as an output. So the numerator here becomes c minus c over h. And so that's just 0 over h, which is 0. So our intuition was right. We do just get 0 for a derivative of a constant. So this can be a little complicated. It's easy to make mistakes where you see something like pi or e or something like this that doesn't look like just a number you're used to, and then you try to take the derivative of it rather than just remembering that the derivative is 0. So we'll see some examples of this later. So it is something to keep in mind. So our theorem here is if we have a constant, no matter how complicated that constant is, its derivative will be 0. So moving up one level of difficulty here is, what about the function f of x is equal to x? Well, again, this one we know already if we think about it, because this is just the line y is equal to x. And so we know the derivative of that should be the slope of the line, because this is a line. So in this case, if we think of this as y is equal to mx plus b, the m here is just 1. So we expect our derivative here should just be 1. Let's go ahead and verify that with the definition. So in this case, if we take f of x plus h, that's just going to be x plus h, and f of x is just x. So we see x plus h minus x is just h. So I get the limit as h goes to 0 of h over h. Well, that's just the limit as h goes to 0 of 1, which is just 1. So exactly what we expected it to be, using the fact that f of x equals x is just a line. Now we can continue to up the difficulty a little bit. So we record that value here, but we can continue to up the difficulty. And we've seen some of these. For example, we looked at f of x is equal to x squared when we were doing the limit definition of the derivative. And we saw that the derivative of that was just 2x. And more generally, if we have n bigger than or equal to 1, the derivative of that, this is called the power rule. So the power on the x comes down out front, so you get an n out front. And then you subtract 1 from the power. So the derivative is just n times x raised to the n minus 1. So for example here, if I have f of x is equal x to the 5th, then the derivative of this is just 5x to the 4th. So you brought that 5 out front and then subtracted 1 from the 5. So I'm going to give some general rules here. I'll go through one of these in the lecture to show why it's true, but none of them are very hard to prove. So if I have a constant in a function, if I look at the function formed by taking that constant times the function, so maybe my constant is just like 2, and I multiply my function by 2. If I take the derivative of that, it's the same thing as just taking the derivative of the original function and multiplying that by that constant. And similarly, if I have two functions that are differentiable, so their derivatives exist, then if I take the derivative of the sum of those functions, it's just the sum of the derivatives. And similarly, this is the same thing here. If I put a negative there, the f of x, the derivative of f of x minus g of x is f prime of x minus g prime of x. We can also think of that as, instead of writing f of x minus g of x, I could write it as f of x plus negative 1 times g of x, and then we're just combining these two theorems to get the subtraction. So let's go ahead and see an example here. So let's find the tangent line to this function here, where it's f of x is equal to x to the 3/2 plus 2x squared, and we're going to look at the tangent line where x is equal to 4. So first thing we do, let's find a point on the line. So if I evaluate f at 4, I get 4 to the 3/2 plus 2 times 4 squared. So to evaluate 4 to the 3/2, we can write that as 4 to the 1/2, all raised to the 3. We know 4 to the 1/2 is 2, so then 2 raised to the 3 is 8. And then for the second term, I have 4 squared is 16, times 2 is 32. So f of 4 is equal to 40. So the point on my tangent line is 4, 40. And now we can take the derivative. Well, each one of these, if we think of these as two different terms, the x to the 3/2 and the 2x squared, we can use our power rule and then our two theorems we just had. So to get the derivative of x to the 3/2, we bring the 3/2 down and then subtract out front, and then we subtract 1 from the exponent. So that'll give me 3/2 x to the 1/2. And then we know if I'm taking a derivative of a sum, it's the sum of the derivatives. So I can then just take the derivative of 2x squared. Well, that 2 is a constant, so the derivative of 2x squared is the same as 2 times the derivative of x squared. We know the derivative of x squared by the power rule is 2x. So that gives me 4x for that second term. So overall, the derivative is 3/2 x to the 1/2 plus 4x. So you can see this is much nicer than having to try to do this using the limit definition of the derivative. It would have been a mess for this one. So now if I plug in x equals 4 to this, I get a 3/2 4 to the 1/2, so that just becomes 3 because that 4 to the 1/2 is 2. It cancels the 2 in the denominator. And then 4 times 4 is 16. So the slope of the tangent line is 19. And so we put that together with what we found for the point, and the tangent line is y minus 40 is equal to 19 times x minus 4. Okay, so one more example. We'll do more examples than this, and our library will be built a little bit bigger in the lecture. But for this flip class video, we're going to give one more example here. And we're not going to worry about how to calculate this yet. We'll look at this a little bit more later in future lectures. But for now, we're just going to state it as a theorem that if you have the exponential function e to the x, the derivative of e to the x is just e to the x again. So this is a good one to memorize. It's a nice, easy derivative. We'll also look at how we take the derivative of a to the x, where a is just a constant that's not necessarily equal to e.